Hello, Akash. Can you hear me? Akshara. Okay, okay. So please tell others to join. I'll share my screen now. Can you see the screen? Can you see the screen? Okay, Akash. Okay, okay, Anurag. Okay. So where did we stop last class? We were discussing non-homogeneous recurrence relation, isn't it? And that also we had come to the third case, case 3 of non-homogeneous recurrence relations. Did you solve the rest? Did you find the value of the constant C2? Yesterday we had found the value of constant C1. Let us see what the question is. Yes, Stifle, what is the value of constant C2? C1 is equal to 1. Okay. When you put n is equal to, okay, what is the value of C2? When you put n is equal to 0, you get C1 is equal to 1. And then now substitute n is equal to 1 in this equation, and you again get C2 also equal to 1, isn't it? Yes, very good. C2 is also equal to 1. Okay, so now what is our next step? We have to substitute C1 and C2 in this equation, and you will get the particular solution, isn't it? Sorry, we are finding the homogeneous solution. Right? We will be getting the first part, that is homogeneous solution. Homogeneous solution an of h is given by C1 plus C2n r raised to n, or you can even use this formula. C1, I've opened these brackets. This is the homogeneous part. C1 r raised to n plus C2 r raised to n, and instead of C1 I can use A, instead of C2 I can use B, and instead of r I can use alpha 1. Since both roots are same, I can use alpha 1 on both terms, that is alpha 1 raised to n plus B into n into alpha 1 raised to n, because we have two same roots. Okay, and given the initial condition, we are going to find the homogeneous solution, and we had substituted n is equal to 0 in this equation 2. This is our equation 2, and here we had substituted n is equal to 0, and we had got value of C1. Next, when we substitute n is equal to 1, what will you get? When you substitute n is equal to 1, what will you get? A1 is equal to A into 1 raised to 1 plus B into 1 raised to 1. Okay, in the above equation, if we put, then you know A1 is given to be 2, it is equal to A plus B, and we have found out the value of A to be 1, so B is equal to 2 minus 1, and that is equal to 1. Now we have found out the value of A, and we have found out the value of B. A is equal to 1 and B is equal to 1. Therefore, the general form of the homogeneous recurrence relation, homogeneous part is A. I'll write in the form of C1 and C2. The homogeneous solution, if roots are same, then the homogeneous solution is C1 plus C2. I had used A and B instead of C1 here. Here A is same as C1, and B is same as C2. Okay, A is C1 plus C2. What is the rest? C1 plus C2 n the whole into r raised to n, isn't it? Or you can use this formula. That's why I wrote A and B. Instead of this formula, I just used A instead of C1 and B instead of C2, and you can use this formula also. This formula is also the same as 2. Okay. So C1 plus C2n into R raised to n. So this becomes C1 instead of C1, it is A here. I have solved for A. So 1 plus 1 into n into R raised to n. So this is a homogeneous solution. Okay, 1 plus n into R raised to n. Okay, is it clear? Is it clear? So what is the value of R? We have found out the value of R also. So 1 plus 1 into 1 plus n into R is 1, R raised to 1 raised to n. Okay, 1 plus 1 n into, instead of R, I found out the characteristic root also earlier. So this is 1 plus n into 1 raised to n. Okay. So this is our homogeneous an of H. Now we had found out only first part of the solution, that is an of H. Actually, in the total solution we have found out only an of H. Now next we have to find out the particular solution an of P. So this part is over. Next we have to find out the next part an of P, and then we have to add the total two together to get the final solution. So this much in these steps we had found out the value of, we had found out the general solution for the homogeneous part. Okay. This turns out to be 1 plus n, but here since it is in the power of n, we are just putting it as such. Then next, let us go for particular solution. Let us solve for particular solution. So this is given in the notebook. Okay, this question is there in the notebook. This is given here. This homogeneous solution. We had found out the homogeneous solution. So here instead of C1 and C2, I had used A and B. Both are the same. Both formulas are the same. Alpha means R. A means C1. B means C2. So here we had got the value of A and B, or C1 and C2, and I had substituted in the homogeneous equation, and I had got 1 raised to n plus n into 1 raised to n. Okay. Is it clear? Is it clear? If I open these brackets, I will get the answer which is there. That is 1 into 1 raised to n. I get 1 raised to n plus n into 1 raised to n, n into 1 raised to n. This is what is given in the note. Okay. See, 1 raised to n plus n into 1 raised to n. I just opened this bracket. That is 1 raised to n into 1, you get 1 raised to n plus 1 raised to n into n, you get n into 1 raised to n. This is the homogeneous solution. So if since the n term is there, we are not solving for it, we are just putting it as such. Now let us move on to the particular solution. So second part, what we have to, step 2, what we have to do is we have to find the particular solution. Find the particular solution. Now, to find the particular solution, what we are going to do is, given the question given to us is an minus 2 into an minus 1 plus an minus 2 is equal to 2 raised to n. So we know that this is an exponent form. So we have to find out the general solution an is equal to an homogeneous plus an particular. We had found out this part. Next we are going to find out this part. So this there are several cases. When this is a constant, we had one method. When this is a polynomial, we had case two. Now this is an exponent form. Then what we are going to do? So here we find that here we find that the function on the right hand side f of n is equal to 2 raised to n. So this is of the form a raised to n form. So here a is 2. Okay, so this is if f of n is of the form a raised to n, then which method are we going to do? Here a is equal to 2. Okay, a raised to n means the form is a raised to n. So in the given question, when we compare that question and a raised to n, we find that a is equal to 2 here. Okay, so now let us see what to do. Here, in the first part, we had solved for characteristic root, isn't it? What was the characteristic root we obtained for this question when we solved the homogeneous part? What is the characteristic root? R. What did we get the characteristic root for this question? When we solved the homogeneous part, we wrote the characteristic equation and we found the characteristic root, isn't it? What is the value of characteristic root which we got? What is the value of the characteristic root that we got in this question? Very good, Adarsh. 1. So, this is very important. This step is very important. Just remember, from this step onwards, it is very important, okay, in this 2 raised to n case. If it is an exponent form, which is of the form a raised to n, then we have to compare the character, we have to consider the characteristic root when writing the particular solution. We got characteristic root as 1. Now, next step, what you have to do is check if a is equal to r. We have the form 2 raised to n, which is and its general form is a raised to n. This a here given in the question is 2. So write the value of a is equal to 2, and then compare this a with the root we had obtained in the first part when we solved the homogeneous part, the recurrence relation. So here we find that a is 2 and r is 1, which means that a is not equal to r. Okay, a is not equal to r. So therefore, if a is not equal to r, we have to use one formula. If a is equal to r, we have to use another formula to calculate this particular solution. So we have two formulas here, and the two formulas that we should use is by comparing a and r. The a is the value given in the question, the exponent, the base of the exponent 2 raised to n. Then the base, what is given in the question is a. So a is equal to 2, and root is what we found out in the homogeneous part. Compare a and r. We find that a is not equal to r. If a is not equal to r, then our particular solution an of p is equal to a constant p into 2 raised to n. This is our particular solution if a is not equal to r. Okay, if a is not equal to r, then our particular solution is of the form an of p is equal to a constant p into 2 raised to n, and this constant we have to find out and then substitute in this particular equation, say equation 3. We have to substitute in this equation. Suppose if the two roots are same, that is if r is equal to 2, suppose the homogeneous, when solving the when the characteristic equation, we found that the characteristic root is equal to 2, which means that a is 2 and r is also 2. If a is equal to r, then the formula that we have to use is an of p is equal to p into n square into 2 raised to n. So these are the two cases that we are going to solve. In this question, A and R are different, so we will solve with this equation. In the next question, we will consider the case when A is equal to R. If A is equal to R, then the particular solution is given by this formula, that is a constant P into n square into 2 raised to n. Here it is only p into 2 raised to n. But if these two were equal, then the particular solution is p into n square into r raised to n. Okay, so these are the two formulas that we have to study when we consider the third case where the f of n is of the form 2 raised to n. If it is of the form 2 raised to n, then we have two cases. In this third case, this is our third case. 2 raised to n is our third case, or a raised to n, not 2 raised to n. This general form is a raised to n is the case 3. In this case, we have two sub cases. That is, if a is not equal to r and if a is equal to r. If a
ഞാൻ
is not
വിളിക്കുന്നു.
equal to r, what happened? If a is not equal to r, then we use this equation, that is an of p. An of p is equal to p into 2 raised to n. If both are equal, then we use an of p is equal to p into n square into a raised to n. I will write it in the next slide. Okay. Did you understand what I said? See, once more I will say. Case 3. Case 3 of the form f of n is of the form a raised to n. Okay. On the RHS, we have a form a raised to n. Then in case 3, what we have to do is to find particular solution, to find particular solution, you have first check if a is equal to r. R is the characteristic root. R is the characteristic root that we had obtained when solving the homogeneous part. Check if a is equal to r. If it is same, if a is equal to r, then the particular solution an of p is given by p into r raised to n. Okay, p into r raised to n. Is it clear? Sorry, p into a raised to n. It is of the form, the right hand side is of the form a raised to n. So p into a raised to n. Okay, p into a raised to n. Or you can write p into r because both are equal, isn't it? Sorry, when both are not equal, p into uh, a raised to n. If a is not equal to r, then p into a raised to n. And if a is equal to r, then the particular solution an of p is equal to p into n square into a raised to n. Okay, so this you should remember when solving the third case. We have two cases when we consider the particular solution. If the base a, given in the equation, if a is not equal to r, if a is not equal to r, then we have to use the particular solution an of p is equal to p into a raised to n. This p is a constant, where p is a constant. Where p is a constant, and we have to find the value of p and then substitute in this equation to get the final particular solution. Then if a is equal to r, then we have to use an of p is equal to p into n square into a raised to n. And again here you have to find the value of p and substitute in this equation to get the final particular solution. Okay, is it clear? So in this question given to us, we find that a is equal to 2 and the root that we obtained r is equal to 1. So a is not equal to r, which means our particular solution an of p is equal to p into 2 raised to n. That is a raised to n, 2 raised to n. That what is given in the right hand side, you have to write it as such, a raised to n. Here a is 2, it is of the form a raised to n. So here a is equal to 2, so 2 raised to n. What is given in the right hand side, you multiply it by a single constant p. Multiply the right hand side by a constant p, you will get the particular solution. So if a is not equal to r, if a is equal to r, then you have to multiply by one more term, that is n square, p into n square into a raised to n. So these are the two formulas that you have to study here. Now here, since we have an equal case, that is A is not equal to R, we have to solve it and proceed with this equation. So we have a n of p is equal to p into 2 raised to n. Now what I am going to do is, I'm going to take the given question. This is my given question. This is my given question. Now I'm going to substitute for a n as p into 2 raised to n. Then next term is a n minus 1. And I'm going to find out p into 2 raised to n minus 1. And here a n minus 2, I'm going to substitute it as p into 2 raised to n minus 2. And I'm going to find out the value of p. Okay. So in the given equation, on the RHS side, we have to substitute for an minus 1 and an minus 2. And you know an is p into 2 raised to n, an minus 1 is p into 2 raised to n minus 1, an minus 2 is p into 2 raised to n minus 2. So let us substitute. So substituting p into 2 raised to n, that is an of p is p into 2 raised to n into recurrence relation. Okay, that is, this is an of p is equal to p into 2 raised to n. Now what is an minus 1 is equal to p into 2 raised to n minus 1, and a n minus 2 is equal to p into 2 raised to n minus 2. I'm substituting these values the recurrent, all these values into the recurrence relation given. We have LHS. LHS is equal to an minus 2 into an minus 1 plus an minus 2. This is our LHS. Now I'm going to substitute these three in this. I get p into 2 raised to n minus 2 into p into 2 raised to n minus 1, isn't it? Plus p into 2 raised to n minus 2. I'm just, you can eliminate the brackets since everything is multiplication. P into 2 raised to n minus 2 into p into 2 raised to n minus 1 plus p into 2 raised to n minus 2. Okay. Now open these, you can, now what you have to do is just 2 raised to n minus 1 and 2 raised to n minus 2, we have to split it and write. Okay, so it's 2 raised to, what is 2 raised to n minus 1? What is 2 raised to n minus 1? We can write it as 2 raised to n into 2 raised to minus 1. Isn't it? And this 2 raised to n minus 2, we can write it as 2 raised to n into 2 raised to minus 2. So use this formula, you just split it so that we can solve it easily. So you get, that is equal to p into 2 raised to n minus 2 into p into 2 raised to n into 2 raised to minus 1 plus p into 2 raised to n into 2 raised to minus 2. Okay. Is it clear? So what you will get is p into 2 raised to n minus 2 into p into 2 raised to n into this 2 raised to 1, I can minus 1, I can write it as 1 by 2, isn't it? 2 raised to minus 1 is 1 by 2 plus p into 2 raised to n into this 2 raised to minus 2 is 1 by 2 square, and that is 4. Okay, so this is equal to p into 2 raised to n, and this 2 and 2 will get cancelled. You get minus p into 2 raised to n minus p into 2 raised to n. Okay, this is p into 2 raised to n plus p into, oh, sorry, I didn't get it. This is 2 raised to n, right? And I wrote it as n raised to 2. You didn't find this? I had written this as n raised to 2. This is 2 raised to n. Okay. into 2 raised to n into 1 by 4. Now these two terms will plus p into 2 raised to n minus p into 2 raised to n will cancel, and I will get this to be p into 2 raised to n into 1 by 4. Okay. Now I'm going to equate this. This is my LHS, isn't it? This is my LHS. Now I'm going to write the entire equation. I'm going to equate it with RHS. That is, P. When I solve the LHS, I got this part. So P into 2 raised to n into 1 by 4 is equal to the given. In the given question, the RHS is 2 raised to n, isn't it? So now, what next step what I'm going to do is going to compare the coefficients of 2 raised to n on both sides. This is 2 raised to n. I have 2 raised to n on both sides. I'm going to compare the coefficients. So what is the coefficient of 2 raised to n on the right hand side? What is the coefficient of 2 raised to n on the right hand side here? What is the coefficient? What is the coefficient of 2 raised to n on right hand side? What is the coefficient? Please say what is the coefficient of 2 raised to n on RHS? And what is the one? Very good, Typhel. One. Very good, Sriraj. What is the coefficient of 2 raised to n on left hand side? P into 1 by 4. So I can equate the coefficients of 2 raised to n on either side, and I can find the value of P. So what is the value of P? P is equal to, what is the value of P? I'm equating the, comparing the coefficients. In equating the coefficients, I can get the value of P. P is equal to 4, isn't it? I can bring this 4 to this side, isn't it? P is equal to 4. So now I have found out the value of P. Now I can substitute in my particular solution. Finally, I'm going to substitute in my particular solution this constant. Our aim was to find the constant. N of P is equal to P into 2 raised to n was the formula. So now I have found out the value of P, so it is equal to 4 into 2 raised to n. So now I have got the particular solution also. So my total solution, what is total solution? Total solution An is equal to An of H plus An of P, isn't it? I have found out An of H. Earlier we have found out An of H, that is 1 raised to n plus plus 1 raised to n plus n into 1 raised to n is my homogeneous part. We had found out the homogeneous part earlier, isn't it? Do you remember? See, we had found out the homogeneous part here, isn't it? Homogeneous An of H. Now I'm going to add the two solution, homogeneous solution and particular solution, to get the total solution. So this is An of H plus the particular solution I have obtained here, that is 4 into 2 raised to n. So this is my total solution. Okay, so when there are powers of n, if it is 1 raised to n, you have to put it as such. Okay, so that is our total solution. Is it clear? Is it clear? Is it clear to you? That was case 3. Okay, so I had given here in the notes, it is their particular solution. See here, when A is not equal to R, when A is not equal to R, this is our particular solution. Okay, when A is not equal to R, then if A is equal to R, we'll be doing the next question. If A is equal to R, we'll proceed to the next question. When A is equal to R, the formula to be used. What is the formula to be used when A is equal to R? What is the formula to be used when when the root and the given A values are same? When A is equal to R, when A is equal to R, or which formula should be used for particular solution? Homogeneous part is the same always. We have to find the characteristic equation and solve the roots. We will get the roots when we solve the homogeneous part. Compare the root with the given a value, and if a is equal to r, then our particular solution an of p is equal to what? P into n square into a raised to n. Okay, a raised to n is given in the question. Then multiply it with p into n square if a is equal to r. So let us move on to the next question. Question 2, third case 3. Case 3, question 2. Solve the recurrence relation. Solve the recurrence relation. A n plus 2 minus 4 a n plus 1 plus 4 a n is equal to 2 raised to n, where a0 is equal to 1 and a1 is equal to 1. Okay, so this is our equation 1 given question. Or you can, when you write the solution, how can we solve? When when you write the solution, write the equation once again and put it as equation 1. Okay, this is our question only. You write the equation and then put it as 1. So looking at this equation, is it homogeneous? Is it first order? What kind of a relation? Is it linear? What can you say about this recurrence relation? What are the details about the recurrence relation? Hmm? Is it homogeneous? Is this recurrence relation homogeneous? Is this recurrence relation homogeneous? No, very good. Why? On the RHS side, we have a raised to n term. This is of the form a raised to n. Okay, so it comes under case 3. So what we have to do is, we have to find out the homogeneous solution, we have to find the particular solution and add them together to get the total solution. So first let us move on to finding the homogeneous solution. Okay, solution. Step 1, what we find is, find homogeneous solution. Homogeneous solution. Okay, to find homogeneous solution, write the characteristic equation. Characteristic equation. How do you write the characteristic equation? I'm solving this homogeneous part for all questions because you will be able to understand what I'm doing. Okay, what is characteristic equation? To find the homogeneous solution, what you should do first, take the RHS and equate it to 0 so that it becomes homogeneous, isn't it? A n plus 2 minus 4 into a n plus 1 plus 4 into a n is equal to 0. This is the homogeneous equation. Now take the RHS and equate it to 0, you get homogeneous part. Now find the homogeneous solution. To find the homogeneous solution, we have to write the characteristic equation. Now to write the characteristic equation, replace a by r and raise it to the power of n plus 2. Isn't it? What is the characteristic equation you get? What is the characteristic equation? What will you get? R square plus 4 into r plus 4 is equal to 0. To get this equation, what you are going to do? Multiply. Hope you know that step. Or I'll write that once again. What you are going to do? In this equation, replace a by r and raise it to the suffix term. So what you get is, you're going to find the characteristic equation. So you get r raised to n plus 2 minus 4 into r raised to n minus n plus 1 plus 4 into r raised to n is equal to 0. Now next, what we are going to do? What is the next step? To find the characteristic root, what is the next step? What is the next step? Hmm? To get the equation, divide by r raised to n. Divide the entire equation by r raised to n, isn't it? When you divide first term r raised to n plus 2 by r raised to n, you get r square minus 4 into, when you divide r raised to n plus 1 by n, you get r plus r raised to n, r raised to n will cancel, you get 4 is equal to 0. This is the characteristic equation. Now what we have to do? So you have divided by the least power. Okay. The next, you have got the characteristic equation. From this, you have to find characteristic roots. What are the roots? Find the roots. How will you find the roots? See, I'm solving the homogeneous solution. Okay, I'm solving the homogeneous part, which I'm doing it from beginning. So, yes, how did you find? Character r is equal to minus b plus or minus root of b square minus 4ac by 2a. Here, a is equal to 1, b is equal to minus 4, and c is equal to 4. When I substitute this, what I get is r is equal to 4 plus or minus root of 16 minus 16 by 2, and that is I get 2. Very good type you got 2, isn't it? So here we find that this is a second order, the degree is 2. So you will have 2 roots and the roots are same, that is 2. You will have 2 roots and the roots are the same. Okay, so now how will we solve the, what is the homogeneous solution? Now what is the homogeneous solution? What is the equation for homogeneous solution? I have two same roots, isn't it? The it is r square. So since the power degree is 2, you will have 2 roots, and both the roots are 2. So what will you? How will you solve it? Which equation will be used for homogeneous solution? An of h is equal to C1 plus C2n into r raised to n. Okay, or in the note I had given, instead of C1, C2, I had used the terms A and B. So if you open up this bracket, you will get C1 r raised to n plus C2n r raised to n, isn't it? So in my notebook, I had used C1 is equal to A, C2 is equal to B, and instead of R, I had put the term alpha. So when you refer note, you will find that it is of the form A alpha raised to n. This alpha 1, since only one root is there, alpha 1 raised to n plus Bn into alpha 2 raised to n. Sorry, alpha, both roots are same. So you have alpha 1 same. Both are same roots. So you also will have alpha 1. So this is given in the notebook. When you refer notebook, this is the formula used, but it is same as this. Okay, you can use both these formulas. I had written it as C1 plus C2n into R raised to n. So we have two constants, C1 and C2. Here you have to find A or B if you're using this formula. So anyway, I'm proceeding with this C1 plus C2n R raised to n. Instead of R, I had put the symbol alpha. Root 1 is alpha 1. Root 2 is also same, it is alpha 1. Okay. So instead of C1, I had used A. Instead of R, in the note, I had used alpha 1. Instead of C2, I had used B, and R, I had used alpha 1. So which formula is easier for you to remember? Which one should I use? C1, C2 or AB? Both are same. Okay. Which form should I use now? C1, C2 or AB? Okay, very good, Taiful. I'll proceed with AB. Sorry, C1, C2. That's easy to remember. So we have the general form an of the homogeneously an of h is equal to c1 plus c2n into r raised to n. We have one root here, and what is the root that we have got? Root r is equal to 2, isn't it? The root that we had obtained is 2. Okay. So now in this equation we have two constants C1 and C2. We have to find out the value of C1 and C2. We have the value of R as 2. R is given to be 2. R we found out to be 2. Now we have two constant terms C1 and C2. So we have to find out C1 and C2. How will we find out C1 and C2? How will we find out C1 and C2? How are we going to find out C1 and C2? Yes, given initial condition, you have found out C1 to be 1. Very good. Very good. An of H is equal to C1 plus C2n into R raised to n. Now, given A0 is equal to 1. This is given. The initial conditions will be given. Only then we can find out the constants. So given A0 is equal to 1, we get A0 of H is equal to C1 plus C2 n into R is 1, 2 raised to n. So you know A0 is equal to 1. So 1 is equal to C1 plus C2n into 2 raised to n. Isn't it? So what is n? No, I didn't put the value of n. And here n is equal to 0, isn't it? N is equal to 0. And you put A0, we get A0 when we put n is equal to 0. So 0, C2 into 0, the term becomes 0 and you get 1 is equal to C1. Here also n we are going to put as 0. Two raised to 0. This 2 raised to 0 turns out to be 1. This term becomes 0. So you get C1 is equal to 1. Okay, therefore C1 is equal to 1. Now, did you get the value of C2? To find the value of C2, what we should do? Given A1 is equal to 1, you put n is equal to 1. What is the value of C2? Did you find out? Put n is equal to 1. When you put n is equal to 1, what will you get? A1 is equal to what is it? C1 plus C2n into R raised to n. So this n, instead of n, I'm going to put 1. So C2 into 1. Type you are going to get the answer. A1 is equal to 1. Given in the question, A1 is equal to 1, and we had found out the value of C1 also equal to 2 raised to 1. Isn't it? So what is the answer? Huh? So 1 is equal to 2 plus 2C2. Isn't it? What is C2? 2C2 is equal to what is 2C2? 2C2 is equal to minus 1, isn't it? 1 minus this 2 goes to the other side, it becomes minus 1. So C2 is equal to minus 1 by 2. Did you get the answer? Did you get the answer? Typhoon? Adarsh? Anurag? Did you get the value of C2? Okay, C2 is equal to 1 by 2. So now we have got C1 and C2. Now we can write our homogeneous solution, isn't it? What is homogeneous solution? We have solved the first part, homogeneous part. An of H is equal to what? C1 plus C2n into R raised to n, and we have got C1 as 1, C2 as minus 1 by 2, isn't it? C2 as minus 1 by 2, n, and R is 2 raised to n. Isn't it? When we open this bracket, you will get 2 raised to n minus 1 by 2n into 2 raised to n. Okay, this is the answer. This is what we have got in a note also. Even if you put C1 and C2 or A1 and A2, it is the same. Okay, so I have found out the homogeneous solution. Is it clear till here? Oh, the time has exceeded, isn't it? Anyway, next period is also my hour. You can take a break for 5 minutes and come back, okay? After this, we will solve a particular solution. Take 5 minutes break and come back. Don't leave, you can remain here and you can then go and come back. Come back by 11:35, okay? അതാണ് എനിക്കാണ് Hello, please tell others to join back, okay? Hello, hello. So now I'm going to start. So we had found out the first part, homogeneous solution. Okay, we have found out the first part. That is, homogeneous solution is found out. Next, we have to move on to find the particular solution. Okay. So now next step two. Step two, particular solution. To find the particular solution. Now the given equation is a n plus 2 minus 4a n plus 1 plus 4 into a n is equal to 2 raised to n. This is the given question. Okay. So now what is f of n here? What is f of n? What is f of n? What is f of n? What is f of n here? So this is a homogeneous relation, recurrence relation. We have solved the right hand side by equating it to zero. That is, so we got the homogeneous solution. Next, we have to find out the particular solution by solving the RHS. So to solve the RHS, we have to look at which form this RHS is. So this is f of n. That is, f of n is the function given on the right hand side. So f of n is equal to 2 raised to n. This is of the form. This is of the form a raised to n form. Okay, this is of the form a raised to n. So we had solved the homogeneous part and we have got the characteristic root as, what is the characteristic root? What is the characteristic root? When we solved the homogeneous part, we had got one characteristic root, right? What is the characteristic root? Come on first. What is the characteristic root that we had got? Very good, Typhoid 2. Very good, August. We have got 2. Now, next step, what we should do? We have to compare this root with which value should we compare it? With which value should we compare it? I want to write the particular solution. To write the particular before writing the particular solution, I have to compare the characteristic root with a. This is a. It is of the form a raised to n. So this is a 2. You have a is equal to 2, isn't it? In the question, it is of the form a raised to n. So a is equal to 2, and the root r is also equal to 2. So both a is equal to r. So suppose you have two roots. Suppose your roots were here we have got only a single root, but suppose your root where r is equal to 3 and 2. We have two roots, r is equal to 3 and r is equal to 2. If any one root matches with a, we have to use this formula. Okay, any one root. If any one, we have only one root and they are equal. If we have more than one root, if any one root matches with a, then we have to apply this formula only, the same formula. Not only one root, all roots need not be the same as a. If any one root matches with a, then we can use the formula. This formula that we are going to use now. That is, we had written it earlier. A is equal to r is equal to 2. If there are more than one root and if any one root matches with r also, we can proceed the same way. Therefore, a n of p, that is the particular solution, is equal to constant p into n square into this function f of n, a raised to n. Okay, so this is our particular solution. So this is the form of a particular solution. Now what we have to do is look at the right hand side. We have n plus 2, n plus 1 and an. So in this particular solution, in this equation 2, we have to put n is equal an. We have got the value of an as p into n square plus into 2 raised to n. Next put n plus 1, then put n plus 2. So you will get all these three terms. We have already got an. Then put n is equal to n plus 1 in this equation. You will get this term. Then put n is equal to n by 2 in this equation. You will get this term, the third term. Okay. So we can, let us see. Look at the right hand side, find the value of an plus 1 and an plus 2 by substituting values for n is equal to n plus 1 and n plus 2 in this particular solution, and then substitute it here, solve the left hand side, and then equate the coefficient of 2 raised to n on LHS and RHS. The steps again, it is similar to what we had done earlier. Okay. We have an is equal to p into n square into 2 raised to n. So what is an plus 1 is equal to p into n plus 1 the whole square into 2 raised to n plus 1. Then an plus 2 is equal to p into n plus 2 the whole square into 2 raised to n plus 2. Okay. You have an plus 1 and an plus 2. So now what we have to do? We have to substitute in LHS. LHS is equal to an plus 2 plus 4 into an plus 1 plus 4 into an. Okay, now substitute for an plus 1 and an plus 2 here. You will get an plus 2 is this one, that is p into n plus 2 the whole square into 2 raised to n plus 2 plus 4 into an plus 1 is this term. So 4 into p into n plus 1 the whole square into 2 raised to n plus 1 plus 4 into an is this term. So 4 into p into n square into 2 raised to n. So this is LHS. We have to solve this. N plus 2 a plus b the whole square is a square plus 2ab plus b square. This 2 raised to n plus 2 raised to n plus 2, you can write it as 2 raised to n into 2 raised to 2. Likewise, if we expand everything and if we collect all these n terms together, that is on RHS we have 2 raised to n. So we collect all these coefficients together, solve all these terms. Let me show you. Sorry. See, this is what we are doing now. Okay. See, we had reached this step. We had substituted for all these values, isn't it? See, we had reached this step now. This step. Now I had expanded n plus 2 the whole square as a plus b the whole square, a square plus 2ab plus b square into 2 raised to n plus 2 is written as 2 raised to n into 2 raised to 2, and the whole thing is expanded, and then finally when I solve it, what will you get? See, after solving, what I get is some of the terms will cancel off, and then finally I will get 8 p into 2 raised to n. Okay. Is it clear? So when you solve, try to solve it and then finally get this answer. You will be getting that answer. Then, so you will get LHS as 8p 2 raised to n, and your RHS is already 2 raised to n, isn't it? Your LHS, when you solve, you will get 8p 2 raised to n, and that is equal to on RHS also we have 2 raised to n. So now we can equate the coefficients together. So when we solve this, we will get the LHS. What we get is, on LHS we have 8 into p into 2 raised to n, and our RHS given the question is 2 raised to n. Now equating the coefficients, okay, comparing coefficients, what will you get? What will you get? Comparing coefficients, what is the value of p? Comparing coefficients, what was the value of p? Now, coefficient of 2 raised to n on LHS is 8p and on RHS is 1. So, you get p is equal to 1 by 8. Very good. 1 by 8. Now, what we have to do is, we have our particular solution, an of p, substitute this constant in that equation. That is, therefore, an of particular solution is p into n square into 2 raised to n. This is our equation. This is a particular solution since the roots were equal. So that is, we got the value of p as 1 by 8. You get 1 by 8 into n square into 2 raised to n. This is our particular solution. Therefore, our total solution, we have found out the particular solution also. Therefore, total solution an is equal to an of h plus an of p, and that is equal to an of h we have found out earlier, 2 raised to n minus 1 by 2n into 2 raised to n plus 1 by 8. A particular solution is 1 by 8 into n square into 2 raised to n. So this is the third case. And in third case, we have considered two cases when a is equal to r. We had done one question when a is equal to r, and when a is not equal to r, we had solved the second question. Okay. Is it clear? Is it clear to you? So with this, we have come to the end of solving recurrence relation using characteristic equation. So the first method to solve recurrence relation was using characteristic root method, and we had considered solution of both homogeneous and non-homogeneous recurrence relation using characteristic root method. We have solved homogeneous recurrence relation and we had solved non-homogeneous recurrence relation also, and both these recurrence relations we had different cases, and all those cases have been solved. Okay. Now let us move on to the next section of solving recurrence relation using generating function. So the next section is solving recurrence relations using generating functions. We had studied generating functions in the first part. Now we are going to solve recurrence relations using generating functions. Okay, we had studied several generating functions, several standard generating functions. I had told you to by heart certain generating functions. Okay, we are going to make use of all those generating functions here. Okay, now let us solve one question. Question 1. Use generating function to solve the recurrence relation. Use generating function. If the question, if it is given to solve using generating function, then you have to use this method. If it is given to solve using characteristic root method, then you have to follow the one we had completed earlier. Okay, use generating functions. Use generating functions to solve the recurrence relation. Hope you are writing along with me. Your notes should be complete, okay? When I tell you to submit the notes, it should be completed. Because I'm writing it down, and if you're not writing it along with me, then that means you are sitting idle during these classes. AK is equal to 3 into AK minus 1 plus 2. Use generating functions to solve the recurrence relation. AK is equal to 3 into AK minus 1 plus 2. Okay. So let us see how to solve this using generating functions. Okay, solution. You are asked to solve using generating functions. So what is given to us? Given, write the question. AK is equal to 3 into A k minus 1 plus 2. This is what is given to us. Now, we know the generating function, isn't it? Let g of x is the generating function. What is the general form of a generating function? What is the general form of a generating function? What is generating function? We have on generating function general form, isn't it? A0 plus A1x plus A2x square, etc. Isn't it? Isn't it? This is the general form of a generating function which we had studied in the first part. Plus it goes on etc. up to, see, since the kth term is given here, we can write the kth term ak x raised to k plus etc. This is an infinite series, isn't it? This is an infinite series. So this is the general form of a generating function. Now, in the question, oh, sorry, the question, in this question, you have to write this part also, where the initial condition is not A0 is equal to 1. Okay, this is the complete question. Use generating function to solve this recurrence relation where A0 is equal to 1. Okay, the question, in the question, you have to add this also, where A0 is equal to 1. So, given this recurrence relation, this is our generating function. You have to solve this recurrence relation using generating function. So now what is the value of A0? A0 is directly given in the question, isn't it? A0 is given in the question. What is the value of A0? A0 is given in the question itself. What is the value of A0? I had just now told you to modify it, isn't it? Okay, A0 is equal to 1. Very good. So we can substitute for 1 here in this equation. So this becomes A0 is 1. 1 plus A1x plus A2x square plus A3 x cube plus etc. plus ak x raised to k plus it is an infinite polynomial. It goes like this. Okay, why did we do this? Because given a0 is equal to 1, that is how we substituted this value here. Now, next what I am going to do is, if a0 is 1, then what is a1? How will you find out a1? How will you find out a1? See, this is the question given to us, isn't it? So, to find a1, put k is equal to 1 in equation 1. Put k is equal to 1. What is equation 1? ak is equal to 3 into a k minus 1 plus 2. So, when I put k is equal to 1 in equation 1, what I will get? What will I get? I can find the value of A1, isn't it? A1. A0 is already given to us. To find A1, put K is equal to 1 in the given equation. K is equal to 1 in the given equation. You get A1 is equal to 3 into A. K is equal to 1. So 1 minus 1, 0 plus 2. So what is A0? A0 is already given to us, isn't it? A0 is already given to us. So what this becomes? 3, 3 plus 2, isn't it? So likewise, we can find out most of the terms. So now, or I think I can find out using general solution. Okay, this is iterative method. So I think we have to take the general form. So 1 minute. So g of x is equal to 1 a0. A0 is 1, isn't it? G of x is equal to 1 plus a1x plus a2x square plus a3x cube, etc. plus ak x raised to k, etc. So let's stop with this section. So here you have 1 plus, now when you put a0 in equation 1, you get 3 into a0. I'm not substituting the value of a0 now. We'll do it at the end. Okay. Given that a0 is equal to 1, but I'm not substituting that value. So you get 3 into a0 plus 2 into x. So a1, that is given ak is equal to a 3 into ak minus 1 plus 2. When I put k is equal to 1, I get a1 is equal to 3 into a0 plus 2. Okay, I'm not going to substitute the value of a0. I'm just substituting it in this equation as such. That is 3 into a0 plus 2. I want to generate the series first. So instead of a1, I'm going to substitute 3 into a0 plus 2 into this x. So what is a2? What will be a2? When I put k is equal to 2 in this equation, I get a2 is equal to 3 into a into 2 minus 1, that is a1 plus 2. So here instead of a2, what I'm going to write is 3 into a1 plus 2 into x square plus, instead of a3, when I put k is equal to 3, I will get a3 is equal to 3 into a2 plus 2. Okay, so with this I get a3 is equal to 3 into a2 plus 2 into x cube and so on. So I'm not going to substitute the value of a0 a1 here, because if I substitute the value of a0 as 1 here and go on, this method becomes another method called iterative method. Okay, this is iterative method. I'm not going to use iterative method. I'm going to use generating function method. So don't substitute for values. If you substitute for values, then it becomes iterative method. Without substituting, then this method we call it as generating function method. Okay, so this is another method. Substituting values is another method. You don't substitute values here. We just generate series here. So don't substitute for a0 after, only in this case, only for the first direct term we substitute. Others you don't substitute values. Okay. Is it clear? Don't substitute values. Even if a0 is given, you just expand it with a0, a1, etc. because we are going to generate series. So here we will get g of x is equal to 1 plus 3 a0 plus 2 into x plus 3 into a1 plus 2 into x square plus etc. plus 3 into a k minus 1 plus 2 into x raised to k and so on. Okay, so you can write in bracket given ak is equal to 3 into ak minus 1 plus 2. So you get a1 is equal to 3 into a0 plus 2, then a2 is equal to 3 into a1 plus 2, and a3 is equal to 3 into a2 plus 2 and so on. Okay, and we are just in the given equation we are just substituting the value of k as 1. You get this part and you are substituting it here, then for a1. Then next put k is equal to 2, you will get this equation, substitute for a2 here. Then put k is equal to 3, you will get this part, substitute for a3 here and so on. Okay, so take the given equation, substitute for 1, 2, 3, etc. and then find out a1, a2, a3 and substitute in the general equation. Don't, you know that a0 is equal to 1, but don't substitute for a, you know a0 is equal to 1 here, but don't substitute here because that is another method. Okay, we are going to use generating function method. We are not going to follow iterative method. Is it clear to you? We are following generating function method, so we are not going to substitute values. Is it clear? Is it clear till here? Is it clear till here? Should I repeat? Do you want me to repeat it? Okay, so see, you're given a generating function. Sorry, you're given a question like this: ak is equal to ak minus 1 plus 2, and you are asked to find the solve this recurrence relation using generating function. Then first step what you have to do is write the generating function. That is, you know the general form of the generating function is a0 plus a1x plus a2x square, etc. So in the question, it is given that a0 is equal to 1. So whatever is given in the question, you can substitute directly in this equation. Others, you don't find out any values. If you are given a0, you can substitute it directly in the general, in the generating function. So a0 is given to us, you can substitute a0. Then the rest of the terms you write as such. And we have the next term a1, a2, a3, etc. We can substitute for these values from the given equation. So the given equation is this one. Okay, so to find a1, you substitute k is equal to 1. You will get a 3 into a into 3a0, 1 minus 1 0. So 3a0 plus 2. Just substitute that term here. And also for the rest of the terms, you find out the values like that. That is here. A0 is given to us, then A1 is obtained by substituting K is equal to 1, and you will get 3A0 plus 2. So write it here. Then next, put K is equal to 2 in the, this is our given equation. Put K is equal to 2, you will get A2, and that is 3A0, 3 into A1 plus 1, you write it here instead of A2. And if the next term is A3, just write, put K is equal to 3, and you will get 3A2 plus 2, and so on. You get a series like this. Is it clear? Is it clear? Is it clear to you? So, okay. Just write the generating function general form. If any value is given, substitute that value. Here A0 is given, substitute that value. Then for A1, you substitute for K is equal to 1, you get this term K1 here, A1 term here, substitute in generating function, then put K is equal to 2 in this equation, you get A2 term, substitute K is equal to 3, you get A3 term, and so on. So the series looks like this. Okay, the series looks like this. So next what we have to do is, from this series, we have to use generating functions. We had studied several generating functions. We are going to apply generating functions to solve this, and we are not going to substitute values. If you're going to substitute values in this, then it becomes iterative method. We are going to use generating functions to solve this. So now this equation, we can expand, that is 3a0 plus 2 into x. How will you write 3a0 plus 2 into x? You can multiply this x by the inner term. With the inner terms, you get 3a0 into x plus 2x. Isn't it? Like the second term, you get 3a1x square plus 2x square. And so you just open the brackets in this equation. When you open all the brackets, what will you get? You get 1 g of x is equal to 1 plus 3a0x, isn't it? 3a0x plus 2x. This bracket is not needed here. We will group it last. (3a0x plus 2x) plus what is the next term? Next, multiply the next term, 3a1x square plus 2x square, isn't it? Multiply x square with both the terms. You get 3a1x square plus 2x square plus 3a1x square plus 2x square. So what will be the next term? What is the next term? 3a2 x cube plus 3x cube and so on. Isn't it? Isn't it? I am going to open these brackets, multiplying x with both the terms, multiplying x square with the inner terms and so on. So I get this series like this. Now I'm going to modify this series to a form that is 1 plus, I'm going to take this 3x terms outside. I'm going to collect 3x terms outside. So 3x into a0. See, all these terms 3a0, 3a1x, 3a2x, and group it. I'm going to group it together, and I'm taking the term 3x outside. Okay, I'm going to group all these 3a0, 3x terms together, and I'm going to take 3x as common outside. So what will be the remaining? What will be the remaining part? A0 plus a1x plus a2x square plus etc. Isn't it? I'm going to group these three, the 3x, 3a0x, 3a1x square, 3a2x square terms and bringing it together and taking 3x as common and writing the remaining terms. Okay, plus. Now I'm going to group these two terms together, 2x square, sorry, this is 2x cube. 2x cube, two terms together, and I'm going to take 2x outside, and the remaining will be 1 plus x. From 2x, I'm taking 2x square, I'm taking 2x outside, I get x out inside. Then from 2x cube, I'm taking 2x outside, I get x square plus etc. X raised to k minus 1 plus etc. This goes on as an infinite series. Okay, here you get a k minus 1, x raised to k minus 1, and it goes on as an infinite series. Did you understand? I had grouped these three terms together, 3x terms together, and I took 3x as common. Then I grouped the 2x terms together, I took 2x as common outside. Now, next is 1 plus 3x. Now, what is a0 plus a1x plus a2x square? What is a0 plus a1x plus a2x square? Which form is that? It is our g of x, general form of g of x. G of x is a0 plus a1x plus a2x square, isn't it? Plus this 2x into, what is 1 plus x square? What is 1 plus x square? The sequence generated here is 1, 1, 1, 1, isn't it? What is the generating function corresponding to this polynomial? This infinite polynomial, the sequence generated is 1, 1, 1. I've told you, you have to study that sequence, isn't it? What is the generating function corresponding to this particular sequence here? 1 plus x square. Very good, Akash. 1 by 1 minus x. Okay, so 2x into this part turns out to be 1 by 1 minus x. Okay, so this is, now I'm going to bring this g of x term to the left hand side. Here also I have g of x, this side also I have g of x. So I'm going to bring it to the other side. So I get g of x here, this g of x minus 3x g of x is equal to 1 plus 2x by 1 minus x. So these two terms will be here. I'm taking this term to the left hand side. So I get g of x. Now I am taking g of x as common. G of x into 1 minus 3x. 3x is equal to 1 plus 2x by 1 minus x. Now what is g of x? Now what is g of x? Find g of x. How will you find g of x? G of x into 1 minus 3x is equal to 1 plus 2x by 1 minus x. Now solve the right hand side. When you solve the right hand side, what will you get? Is equal to, multiply this 1 minus x with 1, you get 1 minus x plus 2x the whole by 1 minus x. And that is equal to minus x plus 2x, you get 1 plus x by 1 minus x. So that is now from this we find g of x is equal to 1 plus x by 1 minus x into this term will come down, isn't it? 1 minus 3x. So this is our generating function g of x. Okay, 1 by x, 1 plus x by 1 minus x into 1 minus 3x. So when you write this term, see that this is in increasing order of x coefficient. Okay, this is in increasing order. That is, don't write 1 minus x into 1 minus 3x into 1 minus, this is x, then 3x, it goes on increasing. So the order, when you write the denominator order, this is 1 minus x, then the increasing order 1 minus 3x, etc. Don't write it the other way, okay, when you write generating functions. Is it clear till here? Did you get the generating function? Did you get the generating function? Hello? Now again we have next part to solve. Okay, it's a pretty big part. We'll do it in the next class. Okay, we have only found out the generating function. We have to solve this generating function again. Okay. So did you understand how to get the generating function? Just rearrange the terms and bring it to a general generating function form. Okay. Is it clear? Hello? Is it clear to you? Any doubts? Any doubts in this? Akash. If you didn't understand, just ask, okay? Anytime later or in class, you can ask. What we are doing is we are bringing that form to a generating function form, writing the equation, substituting the values of a0, a1, etc. from the given equation, and you are rearranging the terms and bringing it to a form where we know where the generating function is known to us, okay? And then we substitute the generating function. And finally, we have to solve this term g of x. We'll do that in the next class. Now, see your attendance. Number 1.
1,
Okay.
2, 3,
3.
4,
5,
6,
7,
8,
9,
10,
11. Absent. 12.
12,
11 present.
13,
Okay. 13 present. 14 present.
15,
16,
17 present. Next.
18,
18.
18,
Absent. 19.
19,
20 present. 18 present.
21,
21 present.
22,
Present. Okay. 23. Absent. 24. Absent. 25.
26, 27,
What? 27.
27,
Okay.
28,
Okay. 29 present.
30.
Okay.
32.
32 present. 33. 34.
34.
35.
Next.
36.
Next. 37.
38.
37. Okay. 38.
38.
Next. 39 present. 40. Number 40. Absent. 41 present.
42.
Next. 43 present. 44.
44.
45.
46.
47.
48.
49.
49.
Okay. 50 present.
51.
52. 53.
54.
53.
56.
57.
59.
58 present. 9. 60 present. 61 present.
62.
62. 63 present. So absent is number 24. 33. 40.
40%.
Okay, 40 present. So number 24 and 33. Okay, thank you.